students. Now we're getting back into section 2 here, and we're going to kind of get into some of the real meat and potatoes now of these trig functions. We talked about how we could have coterminal angles, and that their sines and cosines and secants and cosecants and such would be the same value based on the fact that we've defined it as where the terminal side or terminal ray of an angle in standard position intersects the unit circle at that point, the x and the y, defining those. So because of that, we have, without even really defining it, we have talked about what are called periodic functions. Sometimes we'll call them cyclic functions. A periodic function, well, it's a function that's periodic. That's a good definition. If f of t plus p is equal to f of t. So you have this value p here, but f of t plus p is going to be the same as t, f of t, for some constant p. And that's true for all values that you plug in there for t. You get the same exact value, the same y value, the f of the independent variable value. The smallest positive value p for which f is periodic is called the period. Most times, most books call it the fundamental period. That's the smallest one, which means multiples of the fundamental period would also be periods, but based on the definition of our textbook, they call the fundamental period the period itself of our function f. Now think about this and how we have defined our trig functions. Our trig functions correspond to that point on the unit circle where our terminal side, once the angle is in standard position, where it crosses the unit circle, that ordered pair, x, y. And because of that, we have periodic functions, or cyclic functions. Now, I don't have a very good drawing here, but if I have this angle theta, that's a theta symbol right there, then theta plus all the way around again, 360, gives me in the same location where my terminal side crosses. So because of that, for sine and for cosine, for secant and for cosecant, the fundamental period is 360 degrees, or 2 pi radians. That means for every 360, every revolution that we add on or subtract on, any integral multiple of our fundamental period here, 2 pi, or 360 degrees, we're going to get the same sine, we're going to get the same cosine, we're going to get the same cosecant for those angles. The fundamental period for tangent and cotangent, they're kind of different because remember, they're a ratio of two functions, is 180 degrees or pi. You have to kind of keep track of this. Those are things you're going to want to remember. Now I've written them out this way, kind of the long way. Remember, 3 dots like that means therefore, the sine of t plus 2 pi is equal to the sine of t. If you add 2 pi or any multiple of 2 pi, and that includes like negative multiples, we're going to get the same value. Not the same angle, but the same value. The cosine of t plus 2 pi is the cosine of t, the cosecant of t plus 2 pi, cosecant of t, and the secant of t plus 2 pi is the secant of t. And here are the two guys that are a little different than the other four because their period is only pi, or 180 degrees. The tangent of t plus pi is the tangent of t, the cotangent of t plus pi is the cotangent of t. Here's a whole bunch more things that you need to keep track of. Now, are these necessarily identities? Well, they're true for every value t. I don't know if they're always listed this way as identities, but you can think of these and you can use these when you're simplifying expressions or evaluating expressions. You can use this idea as well. And we are going to use the idea of the functions being periodic a whole bunch. Here's a kind of a weird simple example here. It says, given that the sine of pi over 8 is the square root of 2 minus the square root of 2 all over 2, and believe it or not, within a couple of chapters, we'll be able to figure this out. Determine the value of the sine of negative 15 pi over 8. Well, because negative 15 pi over 8 plus 2 pi, I'm adding on a revolution there, I'm adding on the fundamental period, I am going to get negative 15 pi over 8 plus 16 pi over 8, get a common denominator, which is pi over 8. So what I'm saying is that the sine of negative 15 pi over 8 is equal to the sine of negative 15 pi over 8 plus 2 pi is equal to the sine of pi over 8. Because I just showed you that this is equal to pi over 8. Now look at this guy right here. Isn't that what I'm showing right here? Same values? So that tells me that the sine of negative 15 pi over 8, which is what I'm looking for, is equal to the sine of pi over 8, which is given to be the square root of 2 minus the square root of 2 all over 2. So we can find sines and cosines and tangents and cotangents of angles using the fundamental period. And again, before calculators became so affordable, we would have to use tables of values, and we'd have to use the idea of coterminal angles and the like to be able to find, using the tables, the sines, the cosines, the 6 trig functions of the angle. Now, with this diagram over here, I kind of wanted to emphasize the relationship here with sine and cosine when you have an angle and you have its opposite. Remember, if it's positive, it's going counterclockwise. If it's negative, it's going clockwise. But I try to draw this so that this angle size here and this angle size here, if I used a protractor, I would get the same measure. It's just that based on the unit circle, this is positive, this is negative. Both of these terminal sides here, remember this is the initial side, both of these terminal sides here intersect, this one at point P, this one at point Q. But if these angles are the same, that means these x values are the same. So notice that this is going to be x and this is going to be x. But these y values, this is going up, this one is coming down, although they're the same absolute value-wise distance, one's going up, one's going down, so this y value might be y, but this would be its opposite. That tells me, remember, we defined the x as the cosine of theta if it's a unit circle. Remember, I got to put the unit circle down, I always forget to do that. And that the y value is the sine of theta. Well, according to this, it's going to have the cosine of theta and the cosine of the opposite of theta. They're going to be the same number. They're going to both be x. Now look, these two guys are the same. So I wrote that right here. Right here, you can see it. Now look at the y's. This y here, this is the opposite of y. And this y was the sine of theta, and this, of course, again, I'm using this angle, the sine of the opposite of theta. These are not the same. These are opposites. So this one and this one are opposites of one another. So that's what I wrote right here. I wrote that this angle is the opposite of this, or this value is the opposite of this value. Now, if you think back to the idea of even and odd functions, remember how if f of the opposite of x was equal to f of x, it was even? That's what I have here. I have cosine being an even function. And also, if f of the opposite of x was equal to the opposite of f of x, it wasn't called an odd function. And that's what I have here. So sine, the trig function sine, is an odd function. In fact, here are the 6 properties. They're all either even or odd. You can see that this one is odd, this one is even, this one is odd. Look at the value here with the negative. This one is odd, this one is even, and this one is odd. So these two guys right here, the cosine and its reciprocal, secant, those are the even functions. The other 4 are odd functions. And we can use these properties to help us simplify expressions. Look at a couple of examples that I've got over here. I have the secant of t minus 2 times the secant of the opposite of t. And I want to simplify this expression. Well, I'm going to go right after this guy right here. Because I have the opposite of t here, I'm going to go down to this guy. The secant of the opposite of t is equal to the secant of t. So I'm going to substitute in, for the secant of the opposite of t, the secant of t. Well, that's 1 secant of t minus 2 secants of t gives me a negative secant, negative 1 secant of t. And I have simplified the expression a little bit. Okay? Over here, I'm going to use the fact, notice here, that sine is a periodic function and its period, its fundamental period is 2 pi. So the sine of 2t plus 2 pi, go back here, should be the sine of t. This should be equal to the sine, in this case it's not a t, it's a 2t. This should be the sine of 2t. This expression here, using this property over here about from the fact that it's periodic. And then if I used, back to here, that the sine of the opposite of t is equal to the opposite of the sine of t, I have the opposite, this time again 2t instead of just a t, but the opposite of it, that this is equal to its opposite, so I'm going to have minus its that's this minus, its opposite of the sine of 2t. Well, subtracting a negative is the same as adding the opposite, so I have the sine of 2t plus the sine of 2t, so that's going to give me 2 sine of 2t, and I have simplified my expression. Now, this is just a couple of examples here of how we can use some of these properties, and involving the period and involving even and odd. There are all sorts of examples when you're simplifying expressions or you're proving trig identities that we're going to be able to call upon these properties to help us to simplify the expressions and to help us verify identities.